Good afternoon, everybody. Let's start. Okay, so today I'm gonna start with numbers. Numbers can be unsigned or it can be signed numbers. Okay, so what does that means? Unsigned numbers means it can be 0 or positive. They can't be negative. Signed numbers means the number can be positive, it can be 0, also it can be negative. Okay. Let me give you an example. If I want to count the number of students we have in the classroom right now, is that signed or unsigned numbers? It has to be unsigned number because it cannot be negative. Very simple. Other things can be positive and negative. Is that okay? That's what I'm saying. Sometimes we need unsigned numbers, sometimes we need signed number. It depends on what you are measuring, what you are counting, and so on. You understand what I'm saying? Okay. Now, for so now, if you have n-bit number, so now if you have an n-bit number, that means the number has n bits. So if n is 3, so the number is 3 bits or 4 bits. We can have numbers with different number of bits, right? So I can say I'm going to use 8 bits or 16 bits and so on. Okay? So if you have n-bit numbers, so I think I'm explaining it here. Okay. So here, what I want you to know, how many different numbers can be represented in n-bit. Okay, the answer is 2 to the power of n. Okay, so as you see here, if n is 3, how many different combinations I can have here? So 2 to the power of 3, which is 8. These are all the different combinations for 3 bits. Is that okay? If they are 4 bits, as you see here, so how many different numbers, different combinations we can have here? 2 to the power of 4, which is 16. And you can see these are all the combinations we have here. For 5 bits, it should be 2 to the power of 5, and so on. In general, for any n, how many different combinations we can have? 2 to the power of n. Is that okay? Okay. So now, in case of unsigned numbers, I'm going to use all these combinations for 0 and positive only. But for signed numbers, I'm going to use this combination for 0, for positive, for negative. Make sense? Okay. So let's start with the unsigned numbers. So in case of unsigned numbers, this is the 0. So this is equivalent to 0. And then here we have 1, 2, 3, 4, 5, 6, 7. Positive 1, positive 2, positive 3, positive 4, 5, 6 until 7. That means in unsigned numbers, if you have n bits, I can have numbers starting from 0 until 2 to the power n minus 1. Here in this case, 2 to the power n is 8 minus 1 is 7. Okay, but how you are telling me? How did you know this is 4? Because this is 5, this is 6, this is 7. How did you know that? Very easy. That's what I explained to you before. You have to multiply each digit by the weight, by its weight. Okay, as I said before, the weight of the first one, the weight is 1. Here, the weight is 2. The weight is 4. So if you get any number like this one here. So here I'm gonna get 4 from here and then 0, 0. 4, 0, and 1 from here. Okay, 5, and so on. Is that okay? So now what I'm telling you, let me summarize what I said. Number one, for any n bit, these are the different combination we have, 2 to the power of n. Okay? By the way, how can I make this combination? How I need it? Because we're gonna need this later. We need it, okay? So if I give you n bits, how can you generate? Someone last time told me, do I need to memorize? No, the answer, you don't need to memorize. You can generate it. Okay? How? I'm gonna tell you how. So look at, there is a pattern here. Look at the pattern. Look at the pattern. For example, if I have here 3 bits, if you look at the first bit here, so look at the pattern 0, 1, 0, 1, 0, 1, 0, 1. Okay, what about the next one? 2 zeros, 2 ones, 2 zeros, 2 ones. What about the next one? 4 zeros, 4 ones. What if I have more? So it's gonna be 8 zeros, 8 ones. What if I have more? 16 zeros, 16 ones. You have a pattern. You got what I'm saying? So same thing if you look here. Look here. So we have here 0, 1, 0, 1, 0, 1. 2 zeros, 2 ones. 2 zeros, 2 ones. 4 zeros, 4 ones. 4 zeros, 4 ones. 16 zeros, 16 ones. That's it. And the total now is 16. Okay. Same thing for 32. So is that okay? Easy, right? So now I'm expecting if you have n bit number, you should know how many different combinations we can have. That's what you should know. That's number one. Number two, you should be able to generate, not memorize it. Okay? Same thing for 4 bits. Should be able to generate them. Also, I'm expecting you understand. If this number is unsigned, you should know what is the minimum number, and maximum number can be represented in n bits. So as I told you, if I have n bit, it can have numbers from 0 until n minus 1. This is the maximum. Okay? So as an example, in case of 3 bits, so I can represent it from 0 until 7. What if my number is greater than 7? Very simple. We don't make magic. You need more bits. Very simple. In 3 bits, if the number is unsigned, the maximum number is 7. Very simple, right? If it is bigger, you need bigger. Let's have another example. For example, if you have 8 bits, okay, that means 8 bits, if the number is unsigned, you can represent it from 0 until 2 to the power 8 minus 1, which is 255. For any number from 0 to 255, 8 bits should be enough. Greater, you have to increase the number of bits. Very simple, okay? And total, you start from 0 until 256. So total, how many numbers you have in total? 255 here. Total, we have 256, which is 2 to the power of 8. Okay, 2 to the power of 8, because you start from 0. You have a question here?
I was asking why the numbers are equivalent on both sides for the 32 numbers on the slide.
Sorry, your question again?
Yes. So
yeah, because I don't have space here, so I moved it this way. So they have to be next to each other.
So with the first or the last most significant bit on the right side being 1. So go to the other column. Wouldn't the most significant
I'm
bit
sorry.
be 1?
This is you're right. I'm sorry. This is my fault. Okay. Yeah, they have to wait. I'm sorry. This is the first time I teach this course, so there are some typos on the slide. Thanks. So I'm gonna fix it and post it again. You are right. So as based on what I explained, yes, you have here 0, 1, 0, 1, 0, 1, 0, 1, 2 zeros, 2 ones, 4 zeros, 4 ones. That's okay. 8 zeros, 8 ones, 8 zeros, 8 zeros here, 8 ones, and then 16 zeros, 16 ones. All right. Okay, I'm gonna fix it. Okay, guys. Thanks. Any question about unsigned numbers? Okay, now let's move to the signed number. How it would be different? Yes, it will be different. Why? Because the whole space, all the combination here, I'm gonna use it for positive, negative, and 0, right? So, for example, here in total we have 8. Is that okay? Out of the 8 we have 0, so 0 already 0. So the remaining becomes 7. So I have 7 numbers. Is that okay? Half of this number should be positive, the other half should be negative. But wait a second, this is an odd number. It can be half and half. It can. That's true. So one of them should be bigger than the other. That's true. That's why you can see The negative is one more. So here, out of the 7 we have here, we're gonna have 4 of them are negative and 3 are positive. Is that okay? So what is the formula? Again, we have a formula here. So let me go here. Again, this is very important, guys. Very, very important. 2 to the power of n gives you how many different combinations we have. So you should learn. Second thing you should learn, how can you generate this pattern? We will use it all the time. Very important. Look at the pattern here. Okay. Number 2. Yeah, look what I'm saying here. If your number is unsigned, so we can have here from 0 until I think this is also a typo. I'm sorry, I'm gonna fix this one. And from 0 until 2 to the power of n minus 1. So minus 1 is here, it's not up here. Okay, so 0 until 2 to the power of n minus 1. I'm gonna fix this one. I'm sorry. Yeah, this is the first time I teach it, so there may be some typos. I'm gonna correct it. Okay, so this is from 0 until 2 to the power of n minus 1. Okay, again, now if you, this is for unsigned numbers. What about signed numbers? What is the range of numbers you have? Okay, we have here, as I said before, for signed numbers, we can use one of 3 different systems. Okay, but like one's complement, second complement, and the other one's called signed magnitude, I guess. But we are going to focus only on second complement system, because as I told you before, second complement is more friendly to the hardware. You got what I'm saying? It's more efficient using hardware. So if I want to do some operation like addition, something like that, it's going to be more efficient to use these systems than the other systems. Okay, so that's why I'm going to just, you can ignore this one, okay, because we're going to focus only on the second complement. It's widely used. Okay, I think all computers now are using this system. Anyway, so if you come here, as I told you, so it's gonna be minus 2 to the power of, this is power n minus 1, negative, until 2 to the power n minus 1 here. This is the range from positive to negative. Okay, give me example. As an example, if n is actually 3 bits. Okay, so now you have from negative 2 to the power 3 minus 1, which is negative 4, okay, until 2 to the power of 3 minus 1 until positive 3. So this is your range, okay? So in 3 bits, I can represent the numbers from positive 3 until negative 4, okay? What if my number is greater than that? Very simple. You have to have bigger space, okay? So it's a limit. There is a limit on how big number you can represent in any bits, yes.
Is it supposed to be 2 to the power of n minus 1, or is it supposed to be 2 to the power n, then minus
1? No, this is correct. You are correct with this one. 2 to the power, this is 2 to the power n minus 1 minus 1 here. Okay. This is exponent. Okay. By the way, 2 to the power of n minus 1, this is actually half of the number. 2 to the power n divided by 2. You can see? I told you all the numbers we have 2 to the power of n. That's all the combination we have. Half of them are going to be negative. Okay? The other half are going to take 1 for 0, and the rest are going to go to for positive. That's why we have 1 positive less. Okay? Let me give you another example. Simply. So now, what if I have, for example, 8 bits? Okay, in case of 8 bits, you can just simply use this formula here. You can see I can have numbers from positive 128 until negative 127. Okay, and how many numbers we have in total? 2 to the power of n, which is 256. And half of 256 is actually 128. And this is half minus 1, because 0. We took 0. Any questions? Is that okay? Okay, now, so now I'm expecting to know, if you have n bit, you should know how many numbers we can have in n bits. I'm expecting to know how can we generate this number. I'm expecting to know for unsigned numbers, you should know what is the minimum, what is the maximum. For signed numbers, also what is the minimum and what is the maximum. Any questions?
I have a question.
Yeah, sure.
So on your positive 128, negative 1.7. Are they supposed to be split? So it's negative 1.2.
Sorry, which one you are referring to?
The one that you just did. Should be.
I'm sorry, yeah, you're right. The negative always is one more. It's my fault, I'm sorry. So this is the negative one, this is a positive one. Sorry. Yeah. The negative always one more. Always for any n bit number. The negative is one more. So this is the negative, this is the positive. Yes. Thanks. Any questions? Okay. Now, so look here, what I want to explain next. Yeah, look at this one here. Okay. Here I'm gonna show you if I have this all the possible combination we have for 3 bits. This one, 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 this one. Is that okay? And then I'm gonna show you, for example, in case of unsigned numbers. So here this one is unsigned number. So this one is 0. This one is 1, 2, 3, 4, 5, 6, 7. Make sense? So if your numbers are unsigned, so I'm gonna interpret this one as 7. I'm gonna interpret this one as 6. This one means 5. Is that okay? How can I do it? If you give me a number in a quiz, and I will do that. I will give you a binary number in a quiz. I'm gonna tell you this number is unsigned. Can you convert it to decimal? How can you do that? Very simple. In case of unsigned numbers, you have to multiply every digit by the weight. For example, let's take this one as an example. The weight is 1, the weight is 2, the weight is 4. So 4 plus 2 is 6. Is that okay? Okay, now let's look at the signed numbers. In case of signed numbers, okay, as I explained before in the 2's complement, you can know if the number is positive or negative from the most significant bit. If the most significant bit is 0, so it is a positive number. So if you look here, let me use a different color. Yeah, so if you look here, this is a positive number, positive number, positive number, positive number. So here, 0, okay, I don't want to say 0 is positive or negative, okay, 0. So anyway, I think most of people consider 0 as positive, but I'm not gonna argue about this. So look here, these are the positive numbers we have. Because after that, we have 1, 1, 1, 1. So these are the negative numbers we have. So we have 3 positive numbers and we have 4 negative numbers. Is that okay? Okay, let me finish. Also, so now, as I told you before, if I give you a number in exam, I will do that. I'm telling you what will be in the quiz. I just want you to understand and do it. Number 1, I give you a binary number. I tell you this is an unsigned number. Convert it to this. This is easy. Just multiply every digit by the weight. Add everything together. Done. Okay. Now, if I give you a binary number, I tell you this binary number is signed. Okay. Convert it to decimal. Okay. Now you need to check. If the number is positive, I have to convert it in the same way I did for unsigned. Multiply every digit by the weight. Okay. That's why you can see here, this number is either in unsigned or unsigned, it's the same value. For positive, it's going to be the same value. Okay. Now, what if it is negative? Now, what if the number is negative? Like this case here. Okay. So, for example, in exam, I can give you this number, and I tell you, for example, I can give you 1, 1, 1. I tell you this number is unsigned. Can you convert it? Yes, it's 1, 2, 4. This is the weight. So this one should be 1 plus 2 plus 4 is actually 7. Correct. Okay. Now, okay, I can give you the same number, and I tell you this number is signed, converted. I told you before, in order to, that's what I said last time, if you want to know, for sure this number is negative something, right? So in order to get negative what? In order to get the magnitude here, okay, you have to calculate the 2's complement of this number. In other words, I have to convert this number from positive to negative. So this one is negative x, I want to get positive x. Once you have positive x, you can follow the same thing we did here because it's going to become a positive number. So what you have to do, you have to calculate the 2's complement of this one, which is actually you flip the bits and then you add 1. So it's going to be 1, 0, 0. So these two numbers are the same, but this is negative and this is positive. And because this number is actually positive 1, so this number has to be negative 1. That's what you see here. So this number is actually negative 1. If you look at positive 1, you find the 2's complement. If you take the 2's complement of this one, you get this. Okay. Conclusion in quiz, that's what I will do in a quiz. I give you a binary numbers. Unsigned, you should learn how to convert unsigned numbers. Easy. Multiply every digit by the weight and everything together. If I tell you it is signed, if it is positive, you do the same thing I just said right now. Multiply every digit by the weight. Okay? Negative, you have to calculate the 2's complement and then multiply every digit by the weight to get the positive version of it. Any questions? Okay, let me tell you something important as well here. So again, we agree, guys, if you have 3 bits, these are the combination you have for 3 bits. Okay, but what I'm gonna do for signed or unsigned, I'm gonna interpret some numbers differently. For example, this one can be 7 if it is unsigned. If it is signed, it's gonna be negative 1. So some combination are going to be interpreted differently. Okay, I told you in case of positive numbers, they are the same. 0. So this is 0 in both cases. This is 1 in both cases. 2 in both cases. 3 in both cases. The difference becomes here. Okay, so the same binary number is going to be interpreted differently. Is that okay, guys? Okay. So now we understand we have something we call unsigned number and signed numbers. Okay. Because the purpose of this course, and that's what you are going to see later, is we need to do operations by the hardware, multiplication, whatever, addition, and other operations that are used by computers by the hardware. So let me ask you a question. If I want to do, for example, multiplication, and then I'm going to send to the hardware 111, how the hardware can understand this one, what I mean by 111, because 111 can mean positive 7 or it can be negative 1. So how the hardware can understand that? Okay, so this is completely different from positive or negative numbers, because if here this is positive, this is negative. For positive and negative, I can know if the number is positive or negative from the most significant bit. But how the hardware is going to represent or interpret this number as positive and do the calculations this way to give me a correct answer, or interpret it as negative 1 and the 2 calculations this way to get me correct answer? The answer is the hardware doesn't know. That is why we should have 2 different hardwares, right? So, for example, I'm going to have a multiplier for unsigned numbers. I have another multiplier for signed numbers. So now we have a separation. You understand what I'm saying? So when I design this circuit, the multiplier for unsigned numbers, I'm gonna consider this one 7. So this one gives me correct answer. We're gonna have another different hardware for signed numbers, so that it can interpret this one as negative 1 and give me correct answer. Is that okay, guys? As I told you before, I used to teach 3130. We teach assembly in this course. Remember me in this course, when you take assembly, they are going to tell you we have instructions for signed numbers, instruction for unsigned numbers, because they are different hardware. You got what I'm saying? So in your program, you know, in program, you decide this number signed or unsigned. And based on that, you have to use this instruction or that instruction. Okay. Any questions? Something last time, some students asking me last time, what? Yeah, this is for 3 bits. What if it's more bits? Guys, anything I explain here is applicable for any number of bits. If I give you example for 3 bits, it doesn't mean it's only 3 bits. You can apply the same thing on 100 bits, 200 bits. It doesn't matter. It's the same thing. You understand what I'm saying? Any questions? Okay, that's what I'm explaining here. If I give you here, I tell you this is an unsigned number, and convert this one. I'm expecting you know how to do it. Okay, and if I give you this number and I tell you this is assigned number done by the 2's complement, okay, because this one is negative, so the result is negative something. I need to find this one, so I can simply calculate the 2's complement of this one, which is 7. After you calculate 7, so this one should be negative 7. Any questions? So you should understand how many combinations of number we have in any bits. You should understand every n-bit number has a limit, has minimum number and maximum number, and you should not exceed this limit. If your numbers are bigger, so you have to use bigger number of bits. Okay. Any questions? Okay. Now I want to talk about something here related to signed and unsigned extension. So what do you mean by extension? I'm going to tell you what I mean. For example, let me give you an example. Here in decimal numbers, okay. For example, in decimal number, we have 27. So we have 2 digits, 27. Is that okay? This is decimal numbers, right? Let me ask you a question. So 27, can I represent it in 3 digits instead of 2? Can I represent it in 3 digits? The answer is yes. How can you do it? How? So 0, 0 to 7, right? So 0 to 7 is actually 27. It's the same thing, right? But I just put it in a bigger space. Is that okay? Okay, wait a second, man. Why are keeping bigger space, bigger space? What kind of space you mean here? Okay. The reason is, look here, guys. When I say 1001, this number, as you will see later in this course, is stored in flip-flops, in hardware circuit. You got what I'm saying? It's stored in hardware circuit. That means if I want to store a bigger number, it has to be a bigger circuit. You got what I'm saying? So here, that's exactly what I mean. So if I want to make an addition, I want to make an adder, for example, for 2 bits. So this one can only add 2 bits to 2 bits, okay? And you want to store the result, for example, in 2 bits. So the hardware is limiting me. The hardware is putting a limit here. How big is the input number and how big is the output number? Because this number is stored in hardware. You understand what I'm saying? Anyway, so now what I'm explaining right now, okay, but let me come to my point. If I have 27 in this map, I tell you, can I store it in bigger space? Bigger space means more number of digits. Yes, just put 0 here. Can you store it in bigger? Yeah, put 0, put 0, put 0, put 0, put 0, put 0, and it's the same number. We agree on that, right? But it has to be in the left, not the right. Okay. But this is 2 bits. Can you store it? Sorry, 2 digits. Can you store it in 1 digit? No, you can't. 27, you can squeeze it and put it in 1 digit. You can't, right? So minimum has to be 2. More is okay. More is okay, but the minimum is 2 digits. What I'm gonna do right now, exactly same thing, but for binary numbers. Got what I'm saying? So if I have a binary number, and this binary number is stored, for example, in 4 bits, can I store it in bigger number of bits? Yes. But another but, okay? I'm not gonna put 0 all the time to get the same numbers. Sometimes you put 0, sometimes you put 1s. I'm gonna tell you why. We agree on what I want to do. What I want to do, I want to get the same number, but in a bigger space. To do that, sometimes you put 0s, you will get the same number. Sometimes you need to put 1s, not 0s. I'm gonna tell you how. I'm gonna tell you how. If you. So let's come to. That's what I'm explaining here. So what I'm explaining here, how can you do signed or unsigned extension? So the word extension here means I want to store the number in bigger space. Okay. For example, let's see how can you do it. Number 1, if your numbers are unsigned, okay. So here you need to add 0s on the left all the time. Just forget. So if your number is unsigned, I want to store it in a bigger space. So this is similar to the decimal number, just put 0s. Yeah. So for example, here the unsigned number 15 is stored in 4 bits. So this is So this is 4 bits. Okay, so this number is 15. Okay, if you don't believe me, so this is 1, 2, 4, 8. You need to do the calculations. Anyway, so this is 15 for 4 bits. Okay, what if I want to extend this number? I want to store this number in a bigger space, and still I get 15. This is the main thing. This is the meaning of extension. I want to get the same number, but after storing it in a bigger space. Very simple, because this number is unsigned, just put zeros. I promise you will get the same number. Okay, that's what I did. So here, if I want to represent the same number in 5 bits, just I put 1 0 more here. If I want to store it in 8 bits, so I'm going to put here 4 zeros here. Any questions? You will get the same number. Let's see. So here, for example, if I want to convert this one, the weight here is 1, 2, 4, 8, 16. Okay, if you do the calculation, you will also get 15. Any questions? Okay, now let's move to the signed numbers. Okay, signed numbers here, if your number is positive, you want to extend it, just to put zeros. But the number is negative, you have to put ones. And I promise you will get the same number. Let me give you an example here. For example, so for example, if this number here, this is number 7, okay, it's number 7 in, so if I want to and this, I'm telling you this number is signed. Again, don't be confused. Signed or unsigned, this is not something you can guess from the number. If I give you a signed number and you want to know if this number is positive or negative, yes, this is something you can guess from the number. Just look at the most significant bit. But signed or unsigned, this is not something you can guess. So, okay, this is something you have to consider in the hardware when you design your hardware. So there should be hardware circuit for both for signed numbers or unsigned numbers, okay? Luckily, what I said is true, accurate all the time. You need hardware for positive numbers, hardware for for signed numbers, hardware for unsigned numbers. However, we have one exception. Addition. In case of 2's complement, I can use the same hardware for unsigned and signed. Only in case of 2's complement. That is why the people like 2's complement. So we like the 2's complement system because, as an exception, in case of 2's complement system, the same hardware can produce correct result if the input, it doesn't matter if the input is signed or unsigned. That's why in 3130, you are not going to be given 2 instructions, addition for signed, addition for unsigned. No, you are going to take only 1 instruction, addition. But it works for both cases. That's why the people like the 2's complement. But when it comes to multiplication and division, we're going to know multiplication, you have signed and unsigned. Division, you have signed or unsigned. That okay? Anyway, so let's come to my point here. Okay, so this is positive 7. If I want to store it in bigger space, just put 0 here. Still, you are going to get positive 7. I didn't change the number. However, if the number is something like that, and this number is signed, so this one is negative 1. Negative 1. If I want to store it in bigger space and put 0, as usually I do, you are going to convert this number from negative to positive. It becomes a completely different number. So the conclusion is, if your number is negative and the sign to extend this number, just to put 1. Is that okay? Usually we say you have to repeat the sign bit. If the sign bit is 0, just repeat the 0. If the sign bit is 1, just repeat the 1. Any question? So I'm expecting now you understand what I mean by extension, what extension means. I'm expecting how can you do extension for signed number and also unsigned numbers. Any questions? Okay, good. So now, that's what I'm saying here, guys. That's what I told you. By using the 2's complement system, I can use the same hardware to do addition for signed or unsigned numbers. Okay, signed or unsigned numbers. But notice, there's a very minor thing here I want to tell you about. If you add, look here. If the addition of 2 signed numbers, okay, with negative numbers represented by the 2's complement, is obtained from the addition of the two numbers, binary addition. 1 plus 1 is 0 normally, including the sign bit. Even the sign bit you have to include in the addition, as you will see right now. But if there is a carry out, you need to ignore it. Okay, so here, if your numbers are signed and you do the addition, okay, just ignore the carry. Okay, so let me tell you the conclusion here, guys. The good thing about the post complement is this is an exception. Okay, usually we need two different hardware, one for signed and one for unsigned. But as an exception, I'm sure right now, if the numbers are signed or unsigned, I can do addition in the same way. You will get a correct result. But if there is a carry out here, just ignore it. Okay, I will show it to you now. So for example, let's have some examples to understand what I'm saying. Here, I want to add these two numbers. This one is -2, this one is -5. I want to add them together. Okay, so here, if I want to do the addition, 0 plus 1 is 1. That's okay. 1 plus 1 is 0, and then we have a carry here. 1 plus 1 is 0, 0, and we have a carry here. 0 plus 0 is 0. Now look at the last one here. 1 plus 1 plus 1 is 1, and we have a carry here. I told you, you need to ignore this carry. You need to ignore this carry. So if you do this way, and just I did binary addition, okay? Similar to what I did before for unsigned numbers. So the same approach, you can use it for signed or unsigned. So I got this result. If you do the conversion, you find this one is -2, this one is -5, -7. It's correct answer. Signed or unsigned, it's correct answer. Okay. Another interesting thing in the post complement, that's why we like the post complement. But now I think most if not all the hardware, you can do a search about that. But as far as I know, most of the hardware now is using the post complement system. Another good thing about the post complement system, the same. Let me just finish this part. The same hardware can also use it for subtraction. Unbelievable. So the same hardware can be used for addition, signed or unsigned, and also for subtraction. Why? Because actually subtraction is just, I can deal with subtraction as addition. Okay, for example, if I want to do this kind of subtraction, okay, it's -6 minus -13. For example, I want to do this subtraction. Actually, this subtraction can be addition. Okay, so it's actually -6 plus 13, right? So the way I can do it is I'm gonna add this number to the post complement of this number. Okay, so again, also the same hardware can be used to do subtraction. However, for subtraction, you have to calculate how can you convert this one to addition. Simple. I have to calculate. I'm gonna add this one to the post complement of this number. Okay. Let me give you an example before we move forward. So for example here, yeah, so here I'm assuming I'm storing this number in 8 bits. So this one is -6, this one is -13. Okay, so all what I'm going to do, as you see here, I want to do this subtraction. This subtraction can be done by addition. So here I think I'm going to add, yeah, so I'm going to convert, I'm going to add -6 to the post complement of this one. Okay, because this is what the negative is doing. As I said before, if you forget what I said before, if you have a number and you calculate the post complement to this number, this is equivalent to multiplication by -5. So if this number is +5, calculate the post complement, I'm going to get -5. If it's -5, I'm going to get +5, and so on. Okay. So that's exactly what it is. So I calculated the post complement to this number, and then I added everything together. I got +7, which is correct. Yes, question here?
Yeah, so Jack, when we were doing the -2 plus the -5, why is it that on the very left addition where we had
Carry?
the one, yeah, the carry
Carry.
of the 1, and we had 1 plus 1 plus 1, why wouldn't we
Ignore this carry?
Yeah, why do we ignore it?
Simply because always we are going to have a carry, because in case of negative number, always these are ones. So always it's ones, 1 and 1. You got what I'm saying? So So always there is a carry coming from here. So here, in order to get the correct answer, you have to ignore, just ignore the step. You got what I'm saying? Any questions? Okay, now I want to talk about another concept, or maybe another thing here we call overflow. Okay, so in English, what overflow means? Overflow, English word, overflow. Overflow means you exceeded the limit. If I have a limit, you exceeded the limit, so overflow, right? So what overflow means, as I told you, or the idea here is, if I have a number in 3 bits, I want to add this number to another 3 bits. Okay, guys? And then I want to store the result in 3 bits. I want to store the result in 3 bits. Is that okay? Can this work all the time? The answer is no, because you are adding. I think someone asked me this question last time. When you add, the number it's going to get bigger. For example, assume the number, and the concept is true in case of signed or unsigned. But let me now just make it easy. I'm going to talk about unsigned for now. So, for example, as I just explained, in 3 bits, you can store, from 0 until 7. Is that okay? From 0 to 7. That means if I put here, for example, 7 and another 7 here, 7 plus 7 should be 14. Can I store 14 in 3 bits? No, you can't. You have a limit. If you do that, we say overflow happens. There is an overflow. So as long as the summation is less than 7, 7 is the limit. So there is no overflow. If the summation greater than 7, that means there is an overflow. Okay? And in this case, by the way, the result you will get is wrong. Why? Because I'm going to get the result in 3 bits, and it is supposed to be in 4 bits, not 3 bits. Because 14 can be stored in 4 bits. 4 bits can store up to 15. You understand what I'm saying? So what happens here, guys? If again, someone can say, yeah, you have a piece of paper, you have unlimited space. Don't think this way. I'm doing a hardware circuit. This hardware circuit is going to store the result in 4 bits or 3 bits. Okay, so I'm limited by the hardware, no more than that. Okay, so what I'm saying, if overflow happens, what overflow means? It means the number needs, because you are doing addition, number get bigger, right? So let's look at this example. For example, here, and I have many examples just to explain the concept. So 1 plus 1 is 0, and then we have here 3 ones is 1, and then we have here 1 here. 3 ones is 1, and then we have a carry here. Carry is 1. Is that okay? So now, if you want to store the result in 3 bits, so what I got here is 1, 2, 4. So I got 6. So 7 plus 7, 6. Right? It's not true, right? 7 plus 7 is not 6. Is that okay? It's false because overflow happened. Because you want to restore the result in 3 bits, and 3 bits are not enough. That's why it's wrong. So overflow happened. Is that okay? So number 1. So now I mix. Same thing for signed numbers, because also signed number have a limit. Okay. For example, in 3 bits here, our limit is -4 until +3. Anything outside this limit is gonna be it will trigger overflow. Okay. Let me ask you a question, just by common sense. If these 2 numbers, okay, have different sign, okay, do you think overflow can happen? Different sign. One of them was positive, the other one is negative. Do you think overflow can happen? No, it can't happen. Why? Because they are not helping each other. Here's the problem. Here the number is going to get bigger. Okay? Because so overflow only can happen if both of them, for sure I'm talking here about sign numbers, if both of them are positive or both of them are negative, because the number is going to get bigger. But if you, for example, I have 10 minus 5. So if I can store 10 in a certain number of bits, and now the number is going to get smaller, so still it's impossible to happen. So anyway, what I'm saying here, by common sense, overflow only happens when the 2 numbers help each other, assist each other because the number get bigger. But in subtraction, or if they have different sign, so the number gets smaller. Okay, so if I have already space to store the numbers, these numbers, the smaller number, the same space should be enough for them, right? Anyway, so now I'm expecting you understand what I mean by overflow. Okay, when I add 3 bits to 3 bits and I want to store the result in 3 bits, right? So now I need to know. Now the question is that number 1, how I can know overflow happened or not? How I can check? So, you understand what I mean by overflow? Any problem here? Okay. Now I'm gonna move to the next thing. The next thing, how can you know if you are doing addition? How can you know if there is an overflow or not? Again, overflow means the number you are getting is a wrong number because you need a bigger space. Okay. How can you know overflow happened or not? I'm gonna tell you. So simply, if your numbers, in case of unsigned numbers, okay, how can you know if there is overflow? Very simple. Once you do the addition, if there is a carry resulted from here, so that means there is an overflow. If the numbers are unsigned, and you do the addition, and there is a carry resulted from the most significant bit, there is a carry here. Okay. Be careful. I'm not saying when I did the addition here, I didn't put this carry as a part of the result. I said just a carry. Because I want to add 3 bits to 3 bits, I want to put the result in 3 bits. And carry is generated. Okay? So if you are adding unsigned numbers and a carry resulted from the most significant bit, that means there is an overflow. If there is no carry, no overflow. Very simple. Just to do the normal addition. If there is a carry resulted, there is overflow. No carry, no overflow. No, okay. Overflow means it's a wrong number. Okay. No overflow means it's a correct number. Any questions? This is for unsigned numbers. Any questions? What about signed numbers? How I can know if there is overflow or not in case of signed numbers? Okay, it's not from the carry. Be careful. I'm very clear. In case of unsigned numbers, look at the carry. If there is a carry, there is overflow. There is no carry, no overflow. Straightforward. Okay. Now let's look at signed numbers. If you are adding signed numbers, how I can know if there is overflow or not? Very simple. Look here, guys. If I'm adding a positive number, it means there is a 0 here. I'm adding to a positive number, that means there is a 0 here. And then I got a negative number. That means there is overflow. There are only 2 cases, either this case or another case. Another case here, I'm adding a negative number to a negative number, and then I got a positive number. Again, the carry is not a part of the number. We call it a carry. It's not a part of the number. Okay. So that means there is an overflow. Man, wait a second. How I can add positive to positive and get negative? What are you saying? Can anyone guess? How I can add positive to positive get 7? How I can add negative to negative get positive? How this can happen? Any guess? It's yes.
You overflow from the positive element into the negative number because they start with the 1.
Yes, it's happening because the result you got here is not true. It's a false. That's why there's an overflow, because it's false. It's not true. You can't say. So same thing here. Okay. So again, in case of signed numbers, if I add positive to positive, I got negative. That means there is an overflow, and this result is not true. If I add negative to negative, and then I got here positive, so it's not true. What if I add positive to positive? Negative to negative, and I got negative? It's true. So if I add negative to negative and I got negative, it's true. If I add positive to positive and I got positive, it is true. What if you add one negative to one positive? Don't even think about overflow. Don't think about it. It will not happen. It will not happen. because the two numbers are not assisting each other. Because I'm saying the number is not going to get bigger. So again, in case of sine numbers, simply look how can you know? So now I'm expecting after what? Let me summarize what I'm expecting from you right now. What I'm expecting from you, I can give you two numbers. I ask you to add them, and then I ask you. I have to tell you in the beginning. This is not something you can guess. I have to tell you in the beginning. This number are signed or unsigned, right? Then I'm asking you to do addition, bit by bit addition, and then I can ask you: is there overflow, signed overflow, or is there overflow or not? If the number is signed, in case of unsigned, also I can ask: is there overflow or not? Right? How can you know? Can I say it for the last time? Very easy. In case of unsigned, if there is a carry here, okay, that means if there is a carry resulted from here, that means there is overflow. No carry, no overflow. Period. Now, what if the numbers are signed? How can you know? Yeah, very simple. Look at the sign. Look at the most significant bit. 0, 0, and then you got 1, make positive to positive. You add positive to positive, you got negative, there is overflow. You add negative to negative, you got positive, there is overflow. Any other case, don't think about it. Any other case, there is no overflow, including adding positive to negative. Don't even think about it. So in quiz, don't waste your time. If I give you these two numbers to add them together, don't think about it. There is no overflow because these numbers are not helping each other. One positive, one negative. Any question? So now I'm expecting from you, what is the meaning of overflow? Okay. Why overflow is going to give you a wrong number? Why you have to catch in software in 3140, you have to catch this error because what you are going to get is a wrong number. You are going to get a wrong number, right? So you have to catch this error. I'm expecting to know if I give you two numbers, I'm expecting to know how if there is an overflow. When I did something like that in 3140, I was expecting students to do what I told them, okay? But usually students do something differently. But I'm okay as long as it's wrong, it's correct, I'm okay. Here I'm telling you if there is a carry, okay? So that means there is overflow. Here I told you positive, positive, negative, or negative, negative, positive, there is an overflow. What the students did is they converted these numbers to decimal and they looked at the result. If the result is correct, there is no overflow. If the result is false, there is overflow. It's correct. Because overflow means I'm gonna get the wrong answer. But just waste of time, you are just because you need to convert, you're wasting time. You can see. The other thing I want to teach here in this part is, okay, now told us overflow means I'm gonna get wrong result. Okay, how can we fix it? How can I fix this overflow? Okay, I'm gonna tell you how. The short answer, or what you have to do here, if I want to fix it, okay, so that means this number, it should not be in 3 bits. I need to extend this number to 4 bits, extend it to 4 bits, and now you are going to be correct, you are happy, I'm happy, you are going to go, everything is okay. Okay, so here what I'm saying, here instead of using 3 bits to add 3 bits to 3 bits, that means because the result here needs 4 bits, 1 bit more, so you have to extend this number to 4 bits, extend this number to 4 bits, and then you have to get the result in 4 bits. Is that okay? How can you do this extension? I have just explained it. In case of unsigned number, just put 0. In case of signed number, you have to repeat that. You have the signed bit. You put here 1. In case of negative, positive, you put 0. Okay? This is what you can do. Okay? Okay. And also, there is a shortcut for unsigned numbers. And unsigned numbers, because if you want to extend here, you have to put 0 and you have to put 0 here. It's not right when you extend. So this carry is gonna come to here. And because this is 0, 0, you add to the carry, so actually the carry will come here anyway. Again, in case of unsigned numbers, I told you what you have to do. You have to store the number in bigger space. So here I am, because always when you do extension, you are gonna put 0, 0 all the time in unsigned numbers. So if I put here 0, I put here 0, and there is a carry here. You are gonna add this carry plus 0, you are gonna get the carry. So as a shortcut in unsigned numbers, you can take the carry and consider it a part of the answer, and it's going to be correct. So if the carry is 1, you just put 1 here, and now if I add 3 bits to 3 bits, I'm going to get 4 bits. Consider the carry part of the answer. This is only true in unsigned numbers. You should not do that in signed numbers. Signed number, you just put here, extends the numbers. Let me give you examples. Just I have a lot of numerical examples to understand what I'm saying here, okay? Yeah, so here I'm explaining the concept of overflow. Here, I'm showing you here, here, for example, we have here 5 bits, 5 or 6. We have 6 bits here. In case of 6 bits and this number are unsigned, we can store number from 0 until 31. 31 is actually 2 to the power 6 minus 1, 6 or 5? 5, right? I'm sorry, 5, okay? So 2 to the power 5 minus 1, which is 31, okay? So if you are here and you add 2, so 1, 2, so I will be here. You're okay, you're okay. I'm explaining why overflow can happen. For example, but if you start from 28 and you add 6, you cross this line, okay? Because 31 plus 1 is 0. This is how binary numbers are. They roll over. What do you mean? I mean, for example, if you add here 1, 1, 1, 1, these are 5, 1, right? So this one is actually 31 here. If you add 1, after 1, 1, 1, 1, it's gonna come 0, 0, 0, 0. And for sure there is a carry here. There is a carry. So you roll out. So after here 1, 1, 1, and then you add 1, you're gonna get 0, 0, 0. Okay. So every time you cross this boundary, overflow is gonna happen. So sure. This may be another way to interpret what's the meaning or how can. So if I start from 28, I add 6, well, you are going to get 2. When you go home, do the calculation, you will get 2. Okay. Why? Because there is a 1 in the carry. We didn't take it into account, so you got 2 because it rules, right? Yes.
So, like other quiz, if we're asked to calculate 1, 1, 1, 1 plus 1.
Okay.
How would you wish for us to like answer that? Would you want like the 0, 0, 0, 0, 0, or would you want us to specify that there's overflow or?
Yeah. So no, it depends on if I'm looking for overflow, I will ask if there is overflow or not. But if I just tell you addition, okay, you need to listen to me. Just do addition. For example, if I add 1, 2, 3, 4, and then I add 1. Okay, so the answer is I'm gonna get the result is 0, 0, 0, and for sure there's a carry here. Carry, which is 1. Is that okay? So the answer is if you do it using the machine, if you add 4 bits plus 4 bits using the machine and put the result 4 bits, you are gonna get 0, 0, 0, 0, and then there is a carry. Okay. If I ask you to correct it, correct. So because this is unsigned numbers, okay, this carry can come here, you will get a correct answer. Because if you do extension, as I have just said, if you do extension this way, this one will be added here, so the carry will come here. This is just an exception. So if you want to correct it, you have to, in case of the general rule, you need to extend the numbers and then do the addition again, you will be okay. But just a shortcut, only for unsigned numbers, you can take the carry as a part of the answer. Okay. So if the correct answer, you have to tell me if I add 5 bits plus 5 bits, I get 5 bits, so I have to get, or 4 bits plus 4 bits, I get 4 bits, so I get 0, 0. That's the result. If you don't use the hardware is going to get you 0, 0, 0, which is not correct. You got what I'm saying? Any questions? Okay. This is exactly the same thing, but for signed numbers. So if you look, this all the numbers we have. So here, this is the boundary. This is a boundary between negative number and positive numbers, and we have a boundary here between positive number and negative number. If you do the addition, if you don't cross the boundary, okay, no overflow. If you don't cross the boundary. So if I add this one to something and it's still here, you are okay. If you add something here, it's still here, you are okay. But when you cross the boundary, okay, for example here, 12 plus 5, I'm gonna get negative 15. 12 plus 5, I'm going to get negative 2 because it's wrong. Cross the boundary. You can see I add positive number to a positive number, I got a negative number. Any questions? Okay, so here I have 3 slides. Just mini example. Maybe I'm gonna give a couple of examples here. I'm gonna leave the nothing is new, just exactly the same concept I'm teaching right now. Just let's do it. For example, here 1 plus 1 is 0, and then we have here 1. I'm doing just binary addition. 1 plus 1 is 0, I have 1, 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 and then we have a carry here. So that's what I get at the end here. 0, 0, 0, and then 1. Is that okay? 1 is the carry. So now let's see. Let me ask you before we look at the answer. Let me ask you, if this number unsigned, is there is overflow or not? Unsigned. Yes, because there is a carry here. There is a carry. Yes, there is overflow. That means if you convert this number to binary numbers, sorry, to decimal numbers, the answer is false. So true. 255. This the first one here is 255. So I added 255 plus 1, I got 0, which is not correct for sure because overflow. Now let's look if these numbers are signed. Is there overflow or not? Let's see. Let's see. The first number here is negative number. The second one is positive. Don't even think about it. No overflow. As long as the sign is different, they are not helping each other. It's not gonna grow. You got what I'm saying? So there is no overflow. And the result you got, for sure, carry is not a part of the result. The result you got is correct. Now, if you do the conversion and you want to see if it's correct or not, yeah, this is a negative 1, this is a positive 1, I got 0. What if I want to correct it? If you want to correct it, in case of unsigned numbers, there is a shortcut in the unsigned number. Just take this carry as a part of the answer. So if you put 1 here, 0, 0, 0, it becomes 256. 256, which is correct. Okay? This is a shortcut. But the correct way, or the just why you consider, or what should happen, I have to extend it 1 bit more. If you extend it 1 bit more, and the 1 comes here, so this one will come here, and you are good. And that's what I'm showing you here. So if you extend 1 more bit here, unsigned by putting 0, I can get a correct answer. Okay? Let's have here. I just again here. This is unsigned extension. That's why I put 0. It's unsigned extension. If they are signed, I would put 1 here. It's unsigned. Okay? Be careful here, guys. Please listen to me. When I added 8 bits to 8 bits, and there was no overflow in case of signed. Think about it. What if I store this number in bigger space? Do you think I'm going to have overflow? No. If 8 bits is enough to store the result, bigger than 8, also it's going to be more than enough. I will be happy, more than enough. You understand what I'm saying? So what I'm saying here, if you extend this 1 more, already 8 bits are enough. I got correct answer, right? If you extend it more, okay. If already 8 bits was enough, 10 bits would be enough, 20 bits would be enough. You just store it in a bigger space to be enough. Okay. Anyway, I give you a lot of examples here. Maybe I'm gonna pick 1 more example, so I want to do something else now. Okay, for example, let's look at this one here. Nothing is new. I just like in slides I put too many examples because the best way to understand this stuff. And that's what I did in chapter 2. If you see chapter 2, I put too many examples. I got them from different books. So because using this example, you can understand exactly what I want to say. So let's look at this example, guys. I want to do normal addition. So 1 plus 1 is 0. Then add 1, 0, 0, 0. Okay, 1 plus 1 is 0. And then we have 1. So if you do the addition, this is the result I got. So I added 8 bits plus 8 bits. I got 8 bits. What about the carry? No carry. So there was no carry here. Okay. So let's now look at overflows. Okay, there is no carry. Let's start with unsigned numbers. No carry, no overflow. Okay, let's check. I don't believe you. Okay, you don't believe me. Let's check. Okay, if the answer is correct, so there is no overflow. Very simple. That's what I did. So here I converted the first one. It was 127. I converted this one. It was 1. This one 128. Okay, it's correct. So no overflow. I know without conversion. I know because there is no carry. Right? Now let's look at the second one. In the second one here, if this number are signed, this is a positive number, I got negative number. It's impossible. I positive negative. Yeah, because it's wrong. It's wrong. Okay? So, and that's exactly true. So what happened here, when I do the conversion, this one was 127, this one was 1, and actually this one was minus 128, which more than the limit. What is the limit for 8 bits? The limit for 8 bits is negative 1, 20. Yeah, think, yeah. So negative 128 until positive 127. Okay, the correct answer was positive 127. The correct answer was positive 127. Okay, but my limit is 127. The correct answer, sorry, 128 is the correct answer. But the limit for 8 bits is 127. That's why I got a wrong number, because overflow. Okay? So anyway, how can you correct it? The very simple way, I can just do extension. So here, because this is a positive, I'm going to add 1 bit here to do extension. If you do the calculation, yeah, this one will be correct. So this one is going to be 128. It's correct. Any questions? Okay, so maybe I have some 8 minutes now. In this 8 minutes, I want to talk about. I want to jump into this part because here I want to explain something related to the lab. I'm gonna next lecture. I'm gonna come explain this one, but for today I'm gonna come to this one to explain something related to the lab. Okay, so here in this, as I told you guys, as I told you in this course, we're gonna do binary circuits, or logic circuits. So what do you mean by logic circuit? The purpose of this course, after you finish this course, you should be able to design something like this one. So here we have binary input. Okay, we have a binary input, we have binary output, and you need to design a logic circuit like this one to do something, addition, comparator, or anything else. Okay, so the purpose of this course, we need to do some functionality. I want to do something, addition, subtraction, multiplication, anything. Okay, and then so we have input binary, we have output binary, and then you need to design the circuit inside. Okay? And the circuit inside here is going to be actually logic circuits. Logic circuits. So now we have some like this one, we call it gates, using gates. Okay, so this gate is actually, we call it AND, as I'm going to explain later. This gate is a NOT or inverter. Okay, so I'm going to explain in details what are these gates, how they work. Now I want to do something. I want to link this course to 2 other courses. Listen to me. I want to link this course to 2 other courses. Let's link to electronics first. Electronics. Here, guys, I'm going to tell you we have a logic gate this way. This logic gate, when I give it logic 0, it's called inverter. Okay, or not gate, not. So, and this is what we're going to do in the coming lab, by the way. So you have a chip. This chip has an inverter. So this logic gate, when you give 0, you get 1. When you put 1, you get 0. Okay, this is how it works. Okay? Every gate is going to work in a certain way. And then in this course, you should learn how can you design a circuit to do some operation hardware. Okay, so now in electronics, so now here you are not going to see electronics. You are not going to see transistors because this is another course. So in reality, to implement this one here, we have 2 different worlds here. So let me have a space. Yeah. So we have 2 different worlds: the logic world, and then we have the physical or electronic world. Okay. For logic circuit here, I'm going to have something like this one. I'm going to tell you I have a logic gate. This gate, when I give it logic 0, I get logic 1. When I give logic 1, I'm going to get logic 0. In electronics, this gate can be implemented using transistors. I'm not going to teach this. I'm assuming we have transistor circuit. When I give it 0, I'm going to get 1. When I give 1, I'm going to get 0. And it's already there. Okay. Same thing when I explain any other gate. So every gate I'm going to explain, I'm going to tell you how this gate behaves for binary numbers Okay? But there is an implementation, electronic implementation for this one, and this outside the scope is going to be in electronics. This electronic implementation is going to tell how this conversion can be done. That's why the hardware will do this operation. Is that okay? But wait a second. You are saying here for sure, because here all the time we're talking about logic. All the time we're going to talk about binary, 0 or 1. What about electronics? Electronics doesn't understand 0 or 1. Electronics can understand current, voltage, something like that. That's true. What happens is that, guys, here in logic, always we have two values, either 0 or 1. Okay? In electronics, same thing. I'm going to have also two values equivalent to 0 and 1. For example, I can use 0 volt for logic 0. I can use 5 volt for 1. That means if you have an inverter this way, okay, I'm going to say, give it 0, you get 1. Give 1, you get 0. Is that okay? In electronics, I have an electronic circuit. It has a transistor, whatever. When I give here 5 volt, 5 volt means 1. 0 volt means 0. This is just an example, okay? So again, in electronics, we are going to use two different voltages. One is going to represent logic 0, the other one is going to represent logic 1. Right, okay? So here, if I give 5 volt, I'm going to get 0 volt. If I put here 0 volt, I'm going to get 5 volt. For sure, it's outside the scope of this course to explain the electronics behind it, what transistor and so on, this is electronics. I'm going to use it binary, 0 or 1. Is that okay? Good. The other course I want to talk about is computer architecture. In this course, I'm going to explain the basic blocks, of computers, like how can you design other addition using hardware, how can you do multiplexer. But I'm not going to teach you how can you put everything together to make a computer, because it's a different course. You understand what I'm saying? So the other thing I want to teach here, just to we still have 2 minutes. What are we doing? 2 minutes. Okay? Every minute is 60 seconds. So we have 120 seconds. Okay? I don't want to talk about, look how many microseconds, how many milliseconds we still have. Okay? So what I'm saying here, guys, we're not going to do, for example, we're not going to do electronics, something like that, because it's outside the scope. But you should understand any circuit we have here, it has electronic implementation. You should understand when I say binary 0, 1, 0, 1, 0, 1, there is an equivalent to them in electronics and voltage. Is that okay? In the coming lab, that means, for example, if this one is an inverter here, I told you inverter means if I give 0, it gives me 1. If I put 1, it gives me 0. Is that okay? That means, and that's what you are going to do in the coming lab. That means if I generate a signal like this one, 0, 1, 0. If I give this one to this inverter, the inverter has to give me something like that, because it's doing inversion, 1, 0, 1. Assuming the 0 here means 0 volt, and the 1 here is 5 volt. Is that okay? So if I give something, and that's what you have to do in the coming lab, if I do something like that, in the input, the output has to be something like this one, but in voltage. Is that okay? However, nothing in the world, nothing, voltage, current, anything, nothing can change from a certain value to another value in 0 seconds. Nothing can do that. There is a time. And in the coming lab, I want you to measure this time. What happens in reality is here, so there is nothing, this is ideal case, okay? In reality, we don't have this case. What happens is that it's gonna take some time to go up, and then it's gonna take some time to go down. This time, we call it rise time, and this time is called fall time. And that's what I want you to measure in the coming lab. So we measure the rise time from 10% until 90%. So the time taken for the signal to jump from 10% to 50%, that's what we call rise time. System can be in nanosecond, microsecond, for sure, that's a very short time. The time from 90% to 10% is called full time, the full time. Okay? This is one thing. The other thing I want to explain, the other thing is, okay, if I have an inverter this way and I put 0 here, do you think I'm gonna get 1 at the same time? The answer is no, there is a delay. We call it propagation delay. So what happens is that if I give this input this way, the output is gonna be shifted for some time because there is a delay. This is something normal, there is a delay, okay? And this is something I want you also to measure in the coming lab. So in the coming lab, if you apply input like this one, you are gonna get an output shifted a little bit like this one. And the time here from 50% here until 50% here is called, this time is actually the propagation delay. So there is some time the gate has to take until give you correct result. See? So here, so it's not gonna be exactly the same time, it takes some time, right? So from 50% to 50%, this is the delay when the signal moves from high to low. We have another delay here, another one here, from here to here, also delay when the signal moves from low to high. So something I want to say here, okay, is for every chip you have, there is a data sheet, okay? So I'm sorry, just quickly. I'm gonna go to chapter 2. So in chapter 2 here, I'm gonna explain it, but because we need it for the lab, just very quick. Just here, I'm telling you here, this is logic chip. So every chip has a data sheet. I posted the data sheet for all the chips you have. It's very recommended to read the data sheet. The data sheet tells you everything about the chip, right? So for example, if you have this is exactly the chip you are getting. If you have chip like this one. So here, this chip has how many inverters? It has 1, 2, 3, 4, 5, 6 inverters. Okay. So if this is the input, this is the output. This is the input, the output. Say are separate. So you have 6. You may not need all of them because just use 1. Okay, you have 6. Also, very important, very, very important. If you just apply input here, you get output, it's not gonna work. You have this, in order for this chip to work, you have to put here what we call a bias. So you have to put here 5 volt and 0 volt here. Okay? When you go to electronics, you understand what I mean by a bias. Okay? So again, in order for this chip to work, you have to put here 5 and you have to put 0 volt here. Once you do that, okay, you can just use it. Okay? Anyway, any questions? You have a question?
Earlier, I was going to ask, why do we start at 10% and go to 90 instead of 0 to 100?
This is okay. This is a metric you can define the way you wanna define it. Okay, but the way you usually it's like a standard way. I'm gonna count it from 10 to 90. If you wanna take it from 0 to 100, that's okay. But usually the standard people are using from 10 to 90. But if you want to count it from 0 to 100, that's okay. The way from 10 to 90.
It's 1 high and 0 low. Explaining low.
This is very good question. Think about it. In logic, there are two different values. In electronics, all what I need is just so, for example, I can say the hardware system will be designed so that 0 volt logic feature. 5 volt or I can use the own. It doesn't matter. I just have 2 values. I can consider one value as logic 0, other value is logic 1, and the hardware has to be designed to give me the solution. Most of the time, the hardware is the normal. But you can do the other way. But most of the chips, that's why I want you to read but for most of the chip, usually it's a low voltage, 0 volt and 5 volt. It's something we discussed. 0 volt and 5 volt. 0 volt for logic 0, 5 volt for logic 1. Yes.
I'm just curious. For the pre-lab, to the lab, do we need to turn that in on iLearn or bring it to class?
iLearn.
iLearn, turn in pre-lab on iLearn?
Yes.
Is it in the same?
Well, this is for lab 0.
Yeah.
For lab 1 should be after the lab.
Oh, we turn in the pre-lab?
Or make it easy. So for all labs, just determine after the lab.
Okay, cool, gotcha.
So I got this kid. Where do we get the other kid?
From the department. ECE department.
It's in the same room.
It's a same floor.
Same floor?
Yeah. but
It's
different
right
rooms.
next to the front door.
ECE department.
Do you know what the first quiz is?
Yeah, I think I'm gonna send you an email about it. I think it's gonna be next week.
You have cycle somewhere?
Yes,
Do you
but
know what that's do?
I will do it. I was busy last week to finish the slides because this is the first time I teach this course.
Yeah.
So I have to develop material, but I'm gonna do it maybe today or tomorrow.
Okay.
Send an email out.
I'm gonna send you. I will lose.
So last week when I went there, she said that they were out of or missing materials to fill up the kits. Do you know if they
For
got more?
discovery board.
Yes. You mean that they were out?
So like walk
The
in.
discovery
Of
lab
some
kit.
material.
Lab kit was a discovery.